All right, welcome to Chapter 4, Linear and Quadratic Functions, Section 4.1, Properties of Functions and Linear Models. Objectives, graph linear functions, definitely. This one, average rate of change. So this might not be something that was emphasized in your previous algebra courses, so it might be something new to some of us. Use the average rate of change to identify a linear function, or just find the average rate of change. And then we do make a big deal in this class about functions, not just linear functions, but functions increasing, decreasing, or constant. And then just building a function if you know something about it. For example, the rate of change or the y-intercept. We'll get to that. All right. So we call this a function, and the book really does use function notation. It's still a function if we just said y equals mx plus b. But function notation, f of x equals mx plus b. And not only is this function notation, meaning we have f of x and we have a function in x, but when you write it this way, you also make the slope visible and the y-intercept visible, and that can be useful. And that's what we see. All right, they do tell us right away the domain is all real numbers, and the range is also all real numbers. It looks like they didn't tell us that part yet, but definitely true. All right, so linear, by the way, the root word is line, so these are functions involving lines. Nothing should be terribly surprising here. Yes, they're going to ask you to graph the function, and they're going to ask you the domain and the range. Again, with lines, unless it's a very unusual line like a vertical line or something like that, the domain is going to be negative infinity to infinity, and the range is going to be negative infinity to infinity. Meaning, again, the domain are the x values I can put in. I can put any x value and not get an error on my calculator. And the range are the y values that you can get out. And yeah, I could get any y value in this function as well. All right. We know the slope is 2. Y-intercept is negative 3. And, well, they're just going to graph it with this graphing technique. Now, this is a graphing technique I don't know that the book has talked about until now. You find the y-intercept, and then you use the slope to find another point. That other point, we know that if the slope is, what was the slope, 2? Yeah. So I think of 2 as a fraction, 2 over 1. And so the change in x is going to be 1, and the change in y is going to be 2, and that finds another point. And by the way, I could do that again. Go over 1 and up 2, find another point, go over 1 and up 2. Now, when students are graphing by hand, finding a bunch of points is actually pretty helpful. If you're graphing on the computer, you just click on 2 points, and the computer software will draw a line that's straight. But we could click on any 2 points. In other words, we could click on this point, and as long as we're clicking on points in the graph, you should have the correct graph. All right. So this idea of average rate of change is essentially the slope. It's the change in y over the change in x between 2 points. Well, actually, the average rate of change would be over, well, it still would be between 2 points, but usually over an entire interval. So they're giving us this example. Use average rates of change to identify a linear function. So basically they're saying if you were given all of these as ordered pairs, this ordered pair, this ordered pair, this ordered pair, this ordered pair, keep on going, right? The question is this a linear function? Now we could draw it and just look at it, or we could actually use average rate of change and calculate them. I'm going to say it doesn't look like it because the way this thing is increasing so dramatically here, but we'll see it. All right, so they plotted those points. Do these points lie on a line? I mean, are they collinear? Well, they certainly are not. So this is not a linear function. And the author says, well, let's prove that. And so the author does the change in y over the change in x. So in other words, the author takes 0.04 and subtracts 0.1. Change in y over the change in x. 1 minus 0. And the other kept on doing that and found all of the average rates of change between all of the points. So if this was point A and point B, the author found the average rate of change between point A and B, or the slope between A and B. To be a very small number, it's 0.03. So that slope is very close to 0, but there's got a little slope to it. By the time we get to the end, the slope is 7.82. So between this point and this point, the slope is much, much steeper. And that feels like common sense when you just look at these, but it's nice that we could see it. Actually, the slope wasn't 7, the slope was 5.69. The value was 7. All right, the change in y over the change in x. So this has a slope of almost 6. And that is certainly not the slope the same as this slope, which was, what was it, 3 over 100 or something? I mean, it was given as a decimal, but the change in y over the change in x, if this went far enough, would be up 3 and over 100, if I were to think of it that way. All right, let's try it again. They're just concluding that last one was not a function, not a linear function. All right, so we have another one that's a linear function, or, well, may or may not be a linear function. And they have this. I guess what they're saying is, what can you buy with $60? You can buy 20 sodas and 0 hot dogs, 15 sodas and 3 hot dogs, 10 sodas, 6 hot dogs, 5 and 9. And what they're doing is they put those in ordered pairs. Sodas, comma, hot dogs. So I put this A, B, C, D here so we can follow along with what's going on. If we were to graph those points, point A would be here, where you had 20 sodas and 0 hot dogs. Point B, point C, point D. So this is not the direction that we expect point plotting to go. Usually point plotting goes from left to right, but just the way the numbers were handed to us, we have this. Now, is that a line? Is it a linear function? It looks like it. Those points look collinear, but we can prove they are by doing the calculation. Change in y over the change in x. 3 minus 0 over 15 minus 20. And you even see that it is a negative slope. Let's see, this was point A and point B. So we just found this slope here. That's equal to the slope between these 2 points, and it's equal to the slope between those 2 points. So we're proving that it's a linear function. We know that functions, when we read functions, they're from left to right. So what that means is the slope is, when the slope is positive, the graph is increasing. When the slope is negative, the graph is decreasing. And when the slope is 0, we call it a constant function. It's not increasing or decreasing. So we have this whole list of functions, and I think the first 3 are pretty straightforward, but actually missing a couple. this one right here, h of z, is 4. Now, hopefully you know how to graph this. Getting rid of the h of z notation, just think of it as y equals 4. Y equals 4 is a horizontal line. And since y equals 4 is a horizontal line, it has a slope of 0, or well, it's constant, or it has a slope of 0. But how do we make that visible? How do we kind of prove that? Actually, I like what the author did here. So the author took h of z. I don't know why it's not h of x, but the author just wanted to, took this and essentially manipulated it to be h of z equals 0 times z plus 4, so it matches up to y equals mx plus b. So m was invisible, but it was 0, because that's the only way you would have no variable here. So if m is 0, that would be a slope of 0, and it would be a constant function, or a horizontal line. Like I said, the rest of them, there was nothing invisible involved here, so I think everyone would know the slope is positive, slope is negative, and react accordingly. I don't really have any models for I could do the model for the last example, but I actually deleted that from my slides here because we don't have any major problems like that, whatever the last example was in section 4.1. So I just leave you with this. If you know the average rate of change of a function, you have a linear function if the average rate of change is consistent. That is section 4.1.